My esteemed listeners, in this session, in this tutorial, we will continue with our the brute force strategy based algorithms, or the algorithms those are designed using brute force way of thinking. And in the previous discussion, we had discussed about bubble sort and selection sort algorithms as the specific examples of sorting algorithms which are designed on brute force strategy, and both of them were proved to be of quadratic complexity. Here, once again, I will recall your memory. Brute force design strategy, will always say to just go about solving the problem without thinking the intelligent way of solving the problem. Number one. Number two, in doing so, this will go all round to solve the problem. Definitely, the algorithms that are designed using brute force strategy will be verbose and will also be consuming more number of steps. Therefore, they will involve with huge time complexity. But however, they have the capability of affirming the correct solution. Okay, that is why they are still in place. Continuing with this technique, we will bring out yet another famous algorithm, that is string matching algorithm. Okay, in a very brute force way. Here we should remember the brute here is a mighty capacity entity, okay, which will never think in an intelligent way. That should be, if we go by the definition, definitely that should be a computer. Anyway, all the algorithms are destined to become programs at the end. Therefore, it is only computers which will take care of them in terms of executing the programs. Therefore, that is a brute. Computer here is a brute. Okay, and as far as string matching algorithm is concerned, it has several applications. It has found a place of sanctity in algorithmic circles, okay, in application circles. Okay, the string matching algorithm is used in spell checkers, in spam filters, in intrusion detection systems, in search engines. When we type some word in the search engine, okay, it is exactly string matching that happens. Plagiarism check, okay, particularly the journals, when we submit papers, or the PhD thesis or any thesis of an MTech student, will always be checked for plagiarism, okay, in order to find whether the person, the author, has copied. Okay, this is in place. Okay, this is in place. Plagiarism check is a must in any universities. Okay, therefore, here what happens is the comparison will take place. Comparison of the things written in a thesis or written in a document will be compared with the references that are available. Huge number of references that are available. Bioinformatics is yet another field where string matching algorithms are put to force, and digital forensics and information retrieval systems. Okay, here we will type a keyword or key, let us say key string or a literal, and a comparison will happen, and the respective references will be made available, okay, upon string matching. Okay, this is how the string matching exercise or string matching algorithms are applied heavily, hugely, and they are used till today. Wherever this word processing happens or pattern matching happens. Here it involves two inputs. One is the text, other one is the pattern. Okay, one is the text and other one is the pattern, and text will be having huge length of consisting of n characters, and pattern will be having m characters. Okay, and here a text need not mean only the text that we conventional text. Text could be an image, text could be a chromosome, and pattern could be a small substring if it is a text, literal text, and it could be a small let us say small object in the image that we want to search, or it may be DNA, this thing, what is that, DNA material like adenine, guanine, cytosine and thymine. Okay, we may search in a string of chromosome. Okay, here text will encompass any huge pervading base or any huge search space, and pattern here is a typical thing, a small thing, a thing of interest that is to be searched in the text. Okay, and then given a string of n characters called text, it may be paragraphs, it may be pages together, okay, and a substring of m characters which is called as a pattern. The problem is all about matching this pattern in the text, if at all it exists. So here the important thing that we should remember here is the text length is n characters and the pattern length is m characters, and n is, okay, too much greater than m, then only we can appreciate the string matching exercise. Okay, m should be sufficiently 2 less than n. Okay, n is great. Okay, n is too much. N, because n connotes a text. Text may run pages together. Text may be paragraphs. In that paragraph, in those paragraphs, and in those texts, you will be trying to find a pattern, the existence or non-existence of the pattern. If it exists, the algorithm can be continued cyclically, applied iteratively to find several occurrences of this pattern. Okay, that is the thing, that is the application. Okay, if it exists, then the algorithm will find the index of the leftmost character of the first matching substring. Okay, from here onwards, the pattern exists. That is the output of the algorithm. So here is the text which starts from t0, okay, to tn-1, and here is the pattern. Okay, in the pattern matching exercise, pattern has moved till here. Okay, it is matching, it is aligned with respect to ti. Okay, this is also reached the ith location over the text, and here it is pj, some other character in between, and this is pm-1. Okay, the algorithm will try to match if this is equal to ti is equal to po, or po is equal to p0 equal to the first character is equal to the character that is found in the text. Okay, and here everywhere if it is equal, if it is matching till here, then it will return the location from where this pattern is recognized, the location on the text from where the pattern is found. Okay, this is what a pattern matching or string matching algorithm would return. Okay, we will go for the next thing, and we will take an example. Before we write an algorithm, we will take an example, okay, 1 or 2 examples, and we will reinforce our idea regarding this particular algorithm. Then we will try writing the algorithm. Okay, Siddhaganga Institute of Technology, of course I have shortened over here for the want of space, is the text. This is the text. Okay, text is lengthier, you can say. Okay, you can see over here it consists of almost 40 characters, I suppose, and we are trying to find Gandhi in this. Okay, Gandhi is the pattern. Okay, Gandhi is the pattern. So Gandhi, Gandhi is the pattern. Yeah, what this algorithm does. Okay, in every iteration, the pattern is aligned with respect to text. Yeah, it is aligned. This is the first iteration. G is compared with S. It's a mismatch. It's a mismatch. Therefore, the algorithm just moves this pattern by 1 character ahead. So G comes over here. So G is compared with I. Once again, it is a mismatch. G will move over here. So G is aligned against D, it's a mismatch. It will move over here. Okay. Now, there is a peculiar situation in this example when Gandhi, the character, the pattern will come and sit in this particular position. G, A, N, D, H, I. Let us say it sits over here. Now, G is matching with G. A is matching with A, N is matching with N, and here there is a mismatch. So before it breaks, the algorithm breaks over here and goes for the further movement. 1, 2, 3, 4. 4 comparisons would have happened. But the pattern will be just moved by 1 character over here, because the algorithm should not miss, if at all, this pattern exists elsewhere. Because G is compared with G, A, and there is a mismatch. And here again the algorithm should be careful, because G comes over here, A is there, and N comes over here. N is aligned with respect to the space in the text. Therefore, 1 comparison, second comparison, third comparison. The third comparison fails. Once again, G will come and sit over here. Okay, this is the thing. Okay, the algorithm moves the pattern character by character. Okay, it will move character by character. Okay, if the mismatch happens in the very first character of the pattern, then it will move. The mismatch may happen anywhere. Okay, if the pattern is found, all the comparisons will be matching. All the comparisons of the characters found in the pattern aligned with respect to text will match. Then it will return from the place, okay, from where the matching happens. The place on the text from where matching happens. Okay, it will return position from where the first character of the pattern matching with the character of the text. Okay, it will return. Okay, that is telling that from here onwards the pattern is found. Okay, that's how it works. That's how it works. We'll take yet another example. Okay, we are searching. Okay, crazy. Okay, gods must be crazy is the example. Okay, when it comes over here, so we will just count. Crazy is the pattern, CRAZY. Crazy is the pattern. Okay, it is aligned over here. C, mismatch. So 1 comparison. C, it moves over here, mismatch. Okay, so second mismatch, third mismatch, fourth one, here also it's a mismatch, fifth one. Okay, 5 comparisons, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, by the time you find crazy here, presence of crazy, 18 comparisons would have been taken place, and the algorithm will return the location where the C is seated in the text. Okay, otherwise it may return 0 or it may return -1. If the pattern is not found, it may return 0 or -1. This is how a string matching algorithm works. Brute force string matching algorithm works. And we will discuss about what could be the worst case input, worst case pattern for this string matching algorithm. Okay, let us say we have thousands of zeros in a string. Okay, in a string, it is possible. Okay, it's not a impracticable example, it's a practicable example. 1000 zeros. Okay, we have 1000 zeros over here. Okay, in a particular, let us say it's an information that is flowing in a channel. Maybe it may be an information flowing in a channel. Therefore we will assume this. The pattern to be searched is, let us say 0 0 0 0 1 1 2 3 4 5 6. Okay, length of the pattern is m equal to 6, n equal to 1000. 1000 zeros are there. Okay, now it is arranged. This is the first alignment. Matching happens 1 2 3 4 5 6. 6 matchings happens, and here it will fail because it is mismatching. So for every moment, in every iteration, 6 comparisons will take place. Okay, in every iteration. But anyway, nowhere the string is found, nowhere the pattern is found. So this case presents some kind of a worst case of input for the string matching algorithm. Okay, essentially we will calculate what is or now how many number of comparisons, because the text is too big, the pattern is also big, and it is a worst case. We cannot calculate manually over here. Either it is not required. Of course, it is not required. We will develop an algorithm, okay, and we will literally find out. We will bring in a formalism to find out as to how many comparisons would take place in the worst case. Okay, it is very simple. Now, honesty is the best policy. Once again, see, this is how it happens. I will be moving over here like this. I will be moving over here. It has a limit up to move up to n minus m. It can move only up to this particular place. I can move, but I can move as the index of this, text. I can move, that is the index I can move up to n minus 1. Had there been no comparison, of course, had there been no comparisons. As it is, I can move simply from here till here. Okay, J can move, a counter, a pointer, okay, which can move over this pattern, can move from 0 to m minus 1 in every alignment. Therefore, whenever the algorithm executes, whenever the algorithm works, there are two counters or two pointers, I and J. I will move with its own limitations. J will also move in every alignment from 0 to m minus 1. It is only I which will be continuously moving, but J will continue to change. So here, for example, best is over here, it is found over here. Okay, best is found, best is the pattern, and best is available in the text also. J will move from starting from 0, 1, 2, 3. Okay, all the 3 character positions it will move, and it will find a matching string, and it will return this is the location from where best is available on the text. But look at the situation somewhere over here. Okay, best is arranged over here in one particular iteration. Best is over here. Okay, and J is moving over here. Okay, it is the first mismatch. First character itself is the mismatch. Then best will be moved over here. Okay, best will be literally sliding one character ahead. Once again, J should be set to 0. Therefore, wherever the mismatch happens, as far as the pattern is concerned, okay, once again another iteration is to be set forth, and in every new iteration, J should receive its initial value should be equal to 0. Okay, and we will continue as to how long this pattern can move, as to how long this J can move. Okay, and we will write a sketch for that. We will write a sketch for this for the sake of clarity. Let us assume that this is the text. Okay, it is coming in an undulating way. Okay, you just pardon me for that. Anyway, I cannot write a straight line over here. This will represent the text. Okay, this will represent the text, and the text length is n characters. That means from here till here it measures n in terms of number of characters. Okay, and here is a pattern. We will select a different color for this. Okay, here is a pattern. The pattern is looking something like this, blue. It can go. Okay, the length of the pattern is, let us say it has come over till over here, and it is seating. Okay, it is being seated, it's being aligned, and this length is, let us say, m. Yeah, we have chosen m to be length of the pattern and n to be length of the text. Okay, and furthermore, the pattern cannot move because the text ceases to exist. Okay, therefore, as far as the number of movements are concerned, if the failure happens right in the first character mismatch, and if the case is the first character mismatch, okay, the very first character being mismatch, then the pattern can move character by character up to n minus m characters, because n is the total length available and m is the length of the pattern. it can come and stand over here, so that by this point of time n minus m movements must have taken place. And if in all the movements, if the first character matching is failure, then when it gets seated over here, then also there is a one comparison that happens. Then also a comparison will take place. Therefore, total number of comparisons in case of first character going for a mismatch is n minus m plus 1. n minus m plus 1. And if in every move, in the worst case, as I told earlier, if there are m comparisons but it is a failure, then there will be m comparisons in every move. Therefore, if you multiply this, it is m into n, total number of comparisons is m into n minus m square plus m. Okay, this is the total number of comparisons that happens. But anyway, we need to consider higher order term. The higher order term here is m into n. M is also n is very big, and m is the parametric length. Okay, the pattern length. Therefore, both of them should be considered. Therefore, this belongs to a big theta of mn. Okay, mn complexity. This is called as quasi quadratic complexity. It is neither quadratic nor linear. Okay, it falls under quasi quadratic complexity. Okay, quasi quadratic complexity, QUASI. Okay, so we have understood as to how the brute force string matching algorithm works. Actually, here the brute, the kind of unintelligent work that is being done here is moving character by character. Okay, that is only the drudgery work or a tortuous work that is being done over here. There are several other algorithms which have been developed using lot of intelligence, and there are algorithms which will provide a long jump for the pattern. Okay, here the jump is only character by character. There are algorithms like Boyer-Moore's algorithm, Horspool's algorithm, okay, Morris-Pratt algorithm. Okay, all these algorithms will provide a bigger jump for the pattern. Therefore, they reduce number of comparisons. Okay, the intelligence will work in a way to reduce the number of comparisons. Here in brute force string matching algorithm, the comparisons will be huge. We can take a literal example and we can just verify. Okay, comparing as to how many comparisons, brute force character comparisons, that will take place. Okay, right. And anyway, to have the clarity of this particular magnitude of number of comparisons, we will take this only. Okay, here 1, 2, 3, 4, 5, 6, 7, 8, 9. Once again, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 30 brute force comparisons will take place. But the pattern is not found. 30 comparisons. The number of characters itself is almost 30. Little more than 30 it may be, I have not counted, and there is no need to count also. But anyway, we should feel in order to have some kind of a feeling for this algorithm, the pattern length should be too much less than the length of the text. Okay, it is something like finding a word in a big paragraph. It is something like finding the presence of a dog style in a big image. The other part of the body is missing, let us say. This is called as pattern matching. Or finding some kind of a cancerous cell in a medical image. Okay, here the finding the presence or absence of a tumor in a very big image. A very big image will become a text, and the tumor will become the pattern. Okay, more generally, this string matching algorithm is also called as pattern matching algorithm. Okay, the pattern could be anything, but for the sake of understanding, we have chosen this example. Okay, right. We will move to algorithm. Okay, before we explain the algorithm and before we trying to understand this algorithm, I will write a small sketch over here. Here is a text of n character length, and here is a pattern I will write in a different color. Okay, the pattern is in a, okay, pattern comes something like this, and it is over here. It has moved up to this particular place. I is also come till over here. J is over here. Okay, J moves like this. Okay, over the pattern. I moves like this over the text, and I can move. Okay, I can move till this location. This location is found where exactly? N minus m. N minus m. Okay, because this is m. Okay, yeah. So therefore, as far as when I is set forth to move, it has a boundary. It can move up to n minus m. And as far as j is concerned, it can move up to m minus 1. If and only if j will move up to n minus m, m minus 1, if and only if all the characters found in pattern will be matching against the characters found in the text. Otherwise, whenever a mismatch happens, the algorithm will go for a different cycle. I repeat, whenever mismatch happens, the algorithm will go for a different cycle. When the algorithm goes for the next cycle, j will be once again set to 0. Okay? Yeah. So that is the idea behind this string matching algorithm. We will just move over here. Algorithm brute force pattern matching. It is named over here. It should carry as a function, as an algorithm, 2 parameters. One is text of 0 to n minus 1, and other is pattern 0 to m minus 1. It implements brute force string matching. Okay, what it does: input a text of n characters and a pattern p of m characters. Okay, here we can indicate, since we want to make our algorithm very non-ambiguous. Okay, n is very much greater than m. Okay, we will hasten to add this. Anyway, output returns the index of the first character in the text that starts a matching substring, if at all string exists, or minus 1 if it could not find. Okay, right. For I equal to 0 to n minus m. Okay, this is the boundary for movement of I, that you know, that has been explained. Okay, I can move from 0 to n minus m. J is set to 0. J is set to 0. Let us say this is the position. This is the position. We have moved, and here we have stopped to understand the algorithm. While j less than m, yes, j can move. Okay, both the things should come true. If j is less than m, okay, that means it can reach only n minus m. M minus 1. Okay, j is less than m, and p of j, each and every character of pattern, is equal to t of I plus j. Do. Okay, if this condition holds good together with this condition, then for all the m minus 1 character, all the m characters, then the pattern is found. J less than m and p of j, let us say p of j somewhere over here, equal to t of I plus j, because I should also move along with j. Remember, I should also move along with j. Okay, therefore t of I plus j equal do. Okay, j equal to j plus 1. J will be incremented in order to pave the way for this index to move further. Okay, let us say it is found. Okay, j will have reached this particular position, that is m minus 1. Okay, so therefore this condition becomes true, and p of j equal to t of I plus j, it is over here. T of I plus j is over here. Both of them are will satisfy. Now j will become j plus 1. Okay, so m minus 1 will become m if the pattern is found. Therefore, and it will be thrown out of the loop because j is not less than m, j equal to m. Therefore, it is this incrementation will never happen. So by the time, if the pattern is found at any location over the text, okay, this will happen. If j equal to m, return I. Okay, you will be returning I only because I is still over there. I is incremented only while comparing. You should remember that also. If j equal to m, return I. Otherwise, return minus 1. Otherwise, return minus 1. otherwise return -1. Okay, that is the thing. So we will try to establish the complexity of this algorithm, okay, theoretically. Okay, the basic operation is comparison anyway. Okay, this comparison, okay, this comparison is executed iteratively than this particular comparison. Anyway, therefore there is one time consuming comparison which is written in the while loop itself. Therefore number of comparisons as a function of input size being the text equal to, okay, there is one comparison in the inner for loop, inner while loop, okay, one comparison. This moves from j equal to 0 to m minus 1, j equal to 0 to m minus 1. Okay, this iteration happens several times. Okay, I equal to 0 to n minus m. Okay, this is the thing that happens. So we will expand this as we did earlier. Okay, so it's not a problem for us. It is m minus 1 minus 0 plus 1. Okay, I will write this will and this will cancel. So what we get is only m, and this is repeated from I equal to 0 to n minus m, and this is the summation symbol that we have to apply. So now you take m out, okay, 1 remains within the sigma, and that is once again expanded. What we expand, how we expand, n minus m minus 0 plus 1, therefore plus 1, right? And if you expand this, it is mn minus m square plus n Cfn. Okay, therefore here a higher order term is mn. Neither you can afford to forget the length of the pattern nor the length of the text. Therefore it belongs to big theta of mn. Okay, a quasi-quadratic complexity, right? Now there are some problems given over here. You please try. I will give the hint also. Given the genome string, find number of character comparisons to search AGCT, adenine, guanine, cytosine and thymine. Okay, it is somewhere over here. Okay, AGCT. Okay, it may be, yeah, it may be present, or it's over here. It's over here. Okay, now if you arrange, okay, I will just give a hint. AGCT, you will adjust over here. It's found here only. It's found here only. 1, 2, 3, 4. Okay, you may want to find its availability in some other location. You can just reapply the algorithm. Okay, you put the algorithm itself in a loop. Okay, then it will give you, and set a counter. Okay, counter will take care of how many times this string will appear. Okay, that's the thing. Okay, anyway for this problem you have to find the number of comparisons when the AGCT is found over here, and number of comparisons that would take place when the AGCT TC is found over here. Oh no, AGCT, no, it's not at all available. It's available right in the first place. Okay, write a brute force algorithm for counting number of vowels in a given text. Oh, this is a very interesting thing. Here the pattern, you should remember, the pattern is any one of the characters. Okay, A, E, I, O, U, A, E, I, O, U. Okay, therefore the pattern length is 2 less. Okay, and the text length could be anything. Therefore I will give you a hint in terms of a program. Okay, you can continue with this. That's better. Okay, I will write it over here in this small place. Okay, while okay, the text has not reached its end. Okay, its end is not equal to null character. Okay, null character. Of course I is set to 0. Okay, then you will put a switch will take care. Okay, switch of character, it's a variable. Okay, character, then switch will start CH okay, case small a, okay, case small I, lowercase I, case small o, like this, case capital A, everything you write under the case, and then at the end case A, E, I, O, U. When capital U comes, there you say, okay, vowel plus plus, or yeah, or count plus plus, vowel plus plus, okay, and here you have to necessarily put a break over here, okay, then close this. Default is also not required for this, okay. Anyway you can do that way, right. I told you, and you can translate this into a let us say you translate this into a algorithm. In solving the string matching problem, would there be any advantage in comparing pattern and text characters right to left instead of left to right? So the brute force string matching algorithm suggests that we have to start comparing. I will also move like this, J will also move like this. They will move from left to right, okay. And the question here is there any advantage while I moves in this direction? Yeah, I also moving in this particular direction, J also moving in this particular direction. Is it any advantages? Anyway, the time is not ripe enough for me to tell the advantages. The answer is emphatic yes. Yes. In other algorithms like Horspool's algorithm and Boyer-Moore's algorithm, okay, Morris-Pratt algorithm, we will find the comparison happening from right to left instead of left to right, and these algorithms will provide a bigger jump for the pattern instead of character by character jump, at is character by character sliding, I should say, as it is provided in the brute force string matching algorithm, okay. It is there, and when we go to this comes under trading off space against time, okay. That is the strategy, that is the algorithm design strategy. There we will discuss, we will revisit this brute force string matching algorithm and other intelligible algorithms, okay. And given a bit string of 1000 ones, find the number of bit comparisons in the event of following patterns: 1 1 1 0 1 1 1, okay. This is bit of ones, therefore n is 1000. I will give an explanation only for the first problem, okay. First sub problem, 1 1 1 0, okay. This is a match, this is a match, this is a match, and this is also a match, this is also a mismatch. Once again the sliding will take place. So in every alignment, in every iteration rather, there will be 1 2 3 4 comparisons, okay. 4 into n minus m, n is 1000, m is the length of the string, okay. It is 6, n minus m plus 1. These many comparisons will take place, and you will really appreciate the algorithms which have been written using lot of intelligence, okay, lot of intelligence of course at the cost of space, okay, not consuming these many comparisons. It will happen just like that with minimum number of comparisons, because those algorithms will provide a longer jump for the pattern. So with this we will conclude, and we will take up how exactly combinatorial problems can be solved using brute force design strategy in our next tutorial. Until then, good luck.